first speaker will be Dr. Ken Melville. He's a professor of physical oceanography at Scripps, and his specialty, which is entirely relevant in today's context, is air-sea interactions. Our next speaker will be Dr. Richard Carson. He is a professor in and chair of the economics department at UCSD, and he is also the current president of the Association of Environmental and Resource Economists. Richard specializes in the economic damages of environmental disasters, also pertinent tonight. Perhaps best known for his government work assessing the economic effects of the Exxon Valdez oil spill, he's also well-versed in water projects, including levee systems, having served on a National Academy of Sciences review committee about the topic. Finally, concluding our presentation tonight is Dr. Richard Somerville, a distinguished professor of climate science at the Scripps Institution of Oceanography. He is an expert on global climate change and climate theory and is a specialist in computer modeling of the climate system. And he is the coordinating lead author for the next major climate science assessment report of the Intergovernmental Panel on Climate Change, which will appear in 2007. So without further ado, Ken Melville.
Good evening, and thank you for your introduction, Charlie. I want to talk to you tonight about some of the basics of hurricanes and put hurricanes in a context that I hope will make the subsequent speakers' talks more understandable. And I want to start out with this photograph from space of Katrina on August 28th this year, before it came ashore on the Gulf Coast and did all the damage that we've been reading about for the last 6 weeks or so. In the bottom corner of the overhead, you'll see that there is the cover of a recently published book. It's not my book. It's a book published, written by a colleague at MIT, Kerry Emanuel, who is an atmospheric scientist. And the full title is Divine Wind, The History and Science of Hurricanes. In fact, this is a magnificent book, and if any of you are interested enough to read further on many of the topics that we're going to talk about tonight, I would suggest that you look at this. The photograph also shows some of the main features, some of the obvious features of hurricanes, and that is the circular pattern, in this case in the northern hemisphere, an anti-clockwise circulation. And that has important consequences for a lot of the aspects of damage that we're going to touch on tonight from hurricanes. So the first question is, why is there this cyclonic circulation or an anti-clockwise circulation in the northern hemisphere? In the southern hemisphere, it's clockwise. Now, I think we all know that air likes to flow from regions of high pressure to low pressure, and hurricanes are notable for the very low pressures at their centers. And so in the first instance, if you can imagine air flowing from the boundary of this page in towards the low pressure at the center. However, in a rotating system like the Earth, we have something called Coriolis Acceleration. And if you imagine when you were a child on a merry-go-round, so you were playing with a friend on a merry-go-round and they were sitting directly opposite from you as you spun around, and you had a ball and you tried to throw it to them, what you would find is that instead of them being able to catch the ball had moved relative to their new position because the merry-go-round had been spinning while the ball was in the air. Well, the same thing happens at the surface of the Earth, and because the Earth is rotating, we have this effect called Coriolis acceleration. And in the northern hemisphere, once something starts moving, the Coriolis acceleration will tend to move it to the right. So if we have air coming in from these regions of higher pressure, it will start moving towards the low pressure, and then Coriolis acceleration will tend to move it to the right, and it will veer around in this anti-clockwise circulation. The Coriolis acceleration is named after Gaspard Gustave de Coriolis, a very famous French applied mathematician and engineer. Now, the question then is, this happens a lot. There are lots of low-pressure regions in the atmosphere. Why does a low-pressure region like this, with this anti-clockwise circulation, develop into a hurricane? I think you all know from press reports that hurricanes are associated with warm ocean waters. And typically, temperatures of the ocean greater than about 27 degrees centigrade or around 80 degrees Fahrenheit, or 300 degrees Kelvin. And the top of the atmosphere, or the top of the troposphere, which is where all the weather is at around minus 73 degrees centigrade, or around 200 degrees Kelvin. Now, the fact that the ocean is quite warm can lead to evaporative heat transfer from the ocean into the atmosphere. Now, when you get out of the water on the beach on a day when you have a sea breeze, you might notice that you feel cool. What's happening is that the water that's on your skin is evaporating, and the heat for that evaporation actually is coming from you, and that makes you feel cooler. The same thing happens to the ocean. When the ocean water is warm and the atmosphere is not saturated with moisture, then there can be a heat transfer from the ocean to the atmosphere through the evaporation of seawater, and this is the primary source of energy for hurricanes. Now, once this process starts and you have your winds blowing into that low pressure region, then the increasing surface winds lead to more heat transfer from the ocean, more evaporation, and this then results in convection in clouds. And this is the eye wall of the hurricane here. This is the eye of the hurricane. So the winds are blowing in, spiraling in, and moving in towards the eye, carrying this moisture-laden air, and they start rising. As they rise, the water vapor in the air starts condensing. It gives up this heat of latent heat, and this leads to a local warming of the air, and so that column of air continues to rise. And we end up with a positive feedback, that the wind starts blowing, evaporation occurs, there's convection in these bands of clouds, and that leads to higher winds, more evaporation, and so on, and so on, and so on. And this is called a positive feedback. And this is what leads to the onset of stronger and stronger hurricanes. Now, at steady state, that is when this hurricane is fully formed, then the work done by this thermodynamic heat engine between the atmosphere and the ocean is in fact balanced by the work done by the winds on the ocean, generating waves and currents, and by the energy that's expended in mixing the lower atmosphere near the ocean. Now, we saw an example of this in Katrina. The ocean is the source of this heat, and this is a track showing Katrina as it approached the Gulf Coast. This is the 26th of August, 28th of August, 29th of August, and also shown are the maximum winds in miles per hour, going from 75 miles per hour, 98, reaching a maximum of around 173 miles per hour as it moved through the Gulf of Mexico. Also shown on this figure is what oceanographers call the loop current. This brings warm water in from the Caribbean, and it moves around in a loop like this, goes out through the Florida Straits, and ends up becoming the Gulf Stream. Now, over much of the Gulf of Mexico, the temperature at the surface is approximately constant this time of year or that time of year. But there's a relatively shallow layer of warm water over much of the Gulf, but the warm water in the loop current is much deeper. And this means that there is a lot more heat stored in the ocean under the loop current to fuel a hurricane. And one of the things that hurricanes do is the wind generates waves, the waves break, they mix the surface layers of the ocean, and brings up cool water from below. and that can in fact quench the hurricane. But in the loop current here, that layer of warm water is much deeper, and therefore the prospect of the hurricane being quenched is in fact much less, and as you saw here, in fact it strengthened over the loop current and then decayed a little as it came ashore. So it's this warm water and also the depth of the warm water near the surface that is the fuel for the hurricanes. Now, where do hurricanes form? And here I'm also slipping in the fact that hurricanes are called severe tropical cyclones in some parts of the world, where I come from, and typhoons in the northwestern Pacific, and typically hurricanes in the Atlantic and eastern Pacific. So from what I've shown you so far, it's clear that we need warm tropical waters. We need Coriolis acceleration to get that circulation going and maintain it. And we need a trigger, something to get the whole process going. Hurricanes typically don't form along the equator because there's no Coriolis acceleration at the equator. Now, this is just a summary of the 2004 Atlantic hurricane season. This year's hurricane season isn't finished yet. And after last year's season, we didn't think we would see another season like that in a long time. But surprisingly, or perhaps not surprisingly now, this season looks as though it's going to be just as active, if not more so. Last year, there were 15 named storms. Of these, half a dozen were major storms, Category 3 or above. The strongest storm was Ivan, with a low pressure of 910 millibars and maximum winds of 165 miles an hour. The total damages from last season were about $42 billion. And we know this year that we're going to be well above that, certainly over $200 billion. And the total fatalities last year were approximately 3,000, mainly in the Caribbean. You have seen a lot in the press about the various categories of hurricanes, and there's a scale that ranges from Category 1 all the way up to Category 5. Hurricanes are said to form when the maximum winds reach approximately 74 miles an hour. And also shown here is a storm surge associated with hurricanes by category. So going from Hurricane 1, we can expect a storm surge of 4 to 5 feet, and up to Category 5 with storm surges of 18 feet or more. Just one comment here, a typical Category 3 hurricane with winds in the range of 111 to 130 miles an hour dissipates as energy at approximately the same rate as the average generation of electricity for the whole world. So in one Category 3 hurricane, you're expending as much energy as all the electricity that's being produced in the world. Now, the storm surge, while most people think about high winds when they think about hurricanes, the storm surge is the most dangerous part of a hurricane. In fact, according to the National Hurricane Center, the greatest potential for loss of life related to a hurricane is from the storm surge. And 9 out of 10 people who die in hurricanes are killed by the surge, not by winds. The storm surge with Katrina was approximately 9 meters or 30 feet in Biloxi, Mississippi. It's important to note that much of the development in the US along the Atlantic and Gulf coasts is less than 10 feet above sea level. The storm surge is in fact mainly caused by the wind stress on the water surface, pushing water ahead of the hurricane, and there's also an effect due to the reduced barometric pressure. So just as you suck on a straw, you lift liquid from a glass, when you reduce the atmospheric pressure over the ocean, the local surface level tends to rise, so there's an increase in the water level with the decrease in the barometric pressure. So the storm surge is caused primarily by wind stress piling up the water, especially against the coast and in embayments. A secondary effect is a reduced barometric pressure, and the total depth obviously also depends on the astronomical tides, mainly due to the sun and the moon. And there is also additional damage due to the waves here in shallow water. Now, if you were watching the news broadcasts on the impact of Katrina as it was approaching land and after it hit land, you will recall that there was much emphasis on whether places were to the left or the right of the eye of the storm as it approached landfall. And this is mainly due to this effect. If we consider the hurricane here moving towards land up here, and it's moving with a velocity represented by this arrow, then the winds to the right of the hurricane are the sum of the winds in the circulation plus the motion of the hurricane. So we're in fact adding this to the winds on the right, and the winds to the left, in the front left quadrant, or the left quadrant, are in this direction, but you have to subtract this velocity from the winds going in this direction because they're opposite. So you end up with a significant asymmetry in the wind speed to the right of the eye and to the left of the eye. So as it approaches land, you have enhanced winds in this region here and an increase in the storm surge. To the left here, you may in fact have a reduction in the sea level as the winds tend to blow the water offshore. In addition to doing damage on land, hurricanes can obviously have a devastating effect at sea. And we know from events of the last month and the increase in gas prices that the infrastructure, the oil and gas infrastructure in the Gulf of Mexico has been severely impacted by hurricanes there. And this is typical of the sort of damage. This is a drilling platform in the Gulf of Mexico before and after. We don't have a full report of the height of the waves in the hurricanes this year, but for example, Hurricane Ivan, the largest hurricane from last year, had waves of 90 feet reported, and Hurricane Francis in the same year, we colleagues here at Scripps measured wave heights of 115 feet. How large is that? This is a multicultural demonstration. Well, the BBC does like to consider itself as being a world service. So this is the height of the waves measured in Hurricane Ivan, 91 feet, compared to the Statue of Liberty, a Sphinx, and a London bus. And this is what colleagues here at Scripps measured for waves in Hurricane Francis. I mean, these are large waves. I think it's fair to say that the basics of hurricane dynamics are understood, but there is really a lot of research needed to improve our predictions. Our predictions of hurricane tracks have improved significantly over the last several decades, but our ability to predict hurricane intensity or the potential damage from hurricanes is not as good as we would like. Current research, certainly at Scripps, is focusing on air-sea interaction in hurricane-force winds, and the ocean is the energy source for these hurricanes, so understanding these air-sea interaction processes is vital for improving our ability to predict hurricane strength. And finally, modest research expenditures in this area will give large societal benefits through improved hurricane predictions. Thank you.
One of the issues that I'm going to talk about is, should the economic and social damages of Katrina have been anticipated, what did the government do that exacerbated the hurricane, and why was the emergency response to this hurricane so dreadful, so disastrous? Well, let's look at the impacts here. As hurricanes go, this was a real a biggie. 1,000 plus dead people, 1 million people displaced, $200 billion plus in expenditures that the government is going to cover. The Louisiana Congressional District is asking for $250 billion. Roughly similar amount that's going to be split between the insurers and damages that will go uncompensated. And this is very unusual amongst hurricanes in that this was a very disruptive hurricane because New Orleans is a large port city, disrupted lots of shipping, lots of tourism, came at a dreadful time in terms of energy prices, and last month was the highest jump in inflation in 25 years. So roughly we're looking at about $1 trillion in damages to the U.S. economy. So in this regard, this is a staggeringly damaging hurricane. Well, if we think about New Orleans, there are really two sources of possible large-scale flooding. One of the hurricanes, which we're going to talk mostly about, the other is the Mississippi River. 1927, there was a huge flood on the Mississippi River, and they breached the levees above New Orleans to spare the city from being flooded and displaced 700,000 people. So New Orleans is going to get it from two ways. The prototypical storm here is Hurricane Betsy, which was the last direct hit on the city. It was a Category 4 hurricane, Category 3 when it hit. It was seen as a once-in-a-100-year event. And indeed, the planning of the Army Corps of Engineers was designed around this event to protect it. If we think that this is a Category 4 hurricane, when it comes across, by the time it goes over the land in front of New Orleans, it's going to slow down and it's going to be roughly a Category 3. Well, should we have anticipated that this really isn't a once-in-a-100-year event? Well, there've been fairly good-sized number of near misses since 1950. So if you think about this, this is not really a once-in-a-100-year event. This looks like once in a decade or once in 2 decades sort of event. The key thing here is if we look at this map, Houston, Beaumont, Lake Charles, Lafayette, New Orleans, Mobile, the key thing is all of these places actually lie inland. And they lie inland for very good reasons. Historically, this was about how far you needed to be inland for the storm to die out. The other key thing to note here is that New Orleans, which you often think of as really being on the Gulf, given the direction that hurricanes are coming, isn't really on the Gulf. It's got a fairly substantial landmass out there protecting it. So let's think about the prior government actions. One is oil and natural gas extraction. And what's interesting here is you get an effect like you do with overdrafting water reservoirs. The land in a lot of coastal Louisiana is actually falling. And if you think about rising sea level and falling land, this really picks up the effect when the storm surge that we just heard about comes in. The levee system in the upper Mississippi is denying the nutrients to the wetlands that you need, and the levee system in the lower Mississippi is diverting the water away from building the Mississippi Delta back up, which is historically protected New Orleans. Mostly I'm going to focus on the last 3 issues, which is building in floodplains, which we'll see in a minute, the loss of wetlands and barrier reefs, and what now appears to be the real villain in this story, which is a huge Army Corps of Engineers project called the Mississippi River Gulf Outlet. So this is a picture which pretty much tells the story. So if we think about it, these are all wetlands and barrier islands out here. This is the Mississippi River, which runs down here. And right here is something called the Mississippi River Gulf Outlet. So what's going to happen is that these wetlands here, which are protecting the city, are actually disappearing. So let's look at the design here of New Orleans. New Orleans is really between the Mississippi River, which goes right here, Lake Pontchartrain, the industrial canal, which was the key source of the initial failure, followed by failure of a levee on Lake Pontchartrain. And if we look down here, which we can see better, here's the topology of New Orleans. We can see right here, Gentilly Ridge was effectively where the French Quarter is located. That's the historic part of the city which is above sea level, with two natural levees which made the bowl. And what did they do? They built a flood wall on the Mississippi and one on Pontchartrain, and then they proceeded to fill in with lots of development in areas where if the water ever came in, as they say, it's just a giant bowl. The French Quarter was remarkably came through almost unscathed, as it always has for hundreds of years. So if we think about the cause of the wetlands, a lot of it is just simply engineering, done courtesy of the government. The levee system locally has diverted the Mississippi River and the Delta. The upper Mississippi is funneling lots of water sort of straight through and denying the nutrients and the topsoil, which has always replenished the delta over time. A different cause is that the wetlands south of New Orleans are now cut through with all sorts of channels. Some of this is for shipping, some of it's for agriculture, and some of it is to facilitate oil and gas exploration. This is unfortunately what the wetlands in lots of the areas south of Louisiana look like. So you can see the channels that have been cut for lots of different reasons in the wetlands. And this is causing them to break up at a fairly rapid rate. So we heard about the storm surges, and a crude rule of thumb is to think for every 2.7 miles of wetlands you've got in front of you, you're going to reduce that storm surge when it hits by 1 foot. And so what's happening around New Orleans is you're losing the wetlands at a fairly rapid rate. Since 1930, we've lost 190 square miles of wetlands. We're losing them at roughly the rate of 24 square miles a year. And that's about the average rate. So we're not really doing any better. There's some peaks and spikes. And if we calculated the economic losses that I put out there at, say, $1 to $1.5 trillion, we can see that the government has actually lots of studies to figure out what it would cost to restore the wetlands. And it had, prior to Katrina, decided that the $2 to $20 billion to do it was not really worth dropping the money into it. We can see that that's it would have been much cheaper not to let the wetlands disappear to begin with, and it would have been cheaper to have restored them. Okay, now let's turn our attention to the Mississippi River Gulf outlet. I suspect that prior to Katrina, no one here had ever heard of this. This was one of the two big Army Corps of Engineers boondoggle projects of the 60s and 70s. The other one was the Tennessee Tom Bigby waterway between Mississippi and Alabama. Both of these projects cost billions of dollars and moved more dirt than the Panama Canal. So this is where this comes out on the Gulf of Mexico. This is a huge project. It was designed to shorten the distance between New Orleans and the Gulf Coast. To some extent, it was designed for bigger ships, or at least ships that needed a deeper channel than the Mississippi River, 76 miles long, cut through 40 miles of wetlands. It caused an immediate loss of 30 square acres. And the best thing, at some level, if you read the original environmental analysis of this one, everybody knew that this was a really bad, devastatingly bad project to begin with in terms of what it was going to do. It was at one point forecasted to have a huge amount of traffic on it. It turns out there's virtually no traffic. There's typically 1 to 5 ships a day using it. Mostly it's local barge traffic, and if you look at what it did, it made the industrial land south of New Orleans along this shipping channel very valuable, but it didn't do most of the ships that come up the Mississippi continue to come up the Mississippi because it's in the right location. It's less than 3% of New Orleans traffic. In spite of having at one time been forecast to have a positive benefit-cost ratio, it's taking in $1 million of revenue and costing $22 million, not counting the occasional really big dredging project. If you look at the storm track, if you can remember back to the storm track you just saw, a lot of the simulations now have the water going straight up the Mississippi River Gulf Coast outlet up this channel and breaching the industrial levee, which is in Sector 1. Okay, let's talk now about government response to disasters. It's useful to make a distinction between projects that have a very large scale area. And you can think here big hurricanes, big earthquakes, small to medium-sized nuclear weapons, versus what you would call a narrow strip disaster. The World Trade Center, floods on rivers, lots of smaller earthquakes, most fires. These large-scale spatial area ones, what always happens? Law and order completely breaks down because everything that people have, including food, water, and the basic societal structure has disappeared. In the narrow strip disasters, societal structure and civil order continue to exist on both sides of the disaster. The other thing is conceptually, government agencies have a very difficult time making money in advance of a potential disaster, which could greatly mitigate it, in some instances prevent it. And this goes on, and if you look at the history of hurricanes, most hurricanes do things like veer off and hit the wetlands in front of Lake Charles rather than taking out a major city. And this is one of those things that you almost always have to be ready and spend the money and go through the exercise rather than reacting after the fact. There's also continuing conflict in almost all of the big natural disasters over who's in charge. And in a large area disaster, what happens is the local people are almost always taken out. We had a fairly pathetic scenario of the mayor of New Orleans sitting on the 38th floor of a building with almost no communications, acting as if he were in charge. We had a governor of a state without the resources to control the situation, who wanted to be in charge, and we had the federal government who had the resources, unwilling to give them to the governor of the state unless they could officially take over. And this will play out over and over again. And the only workable scenario is because the governor of a state can't really give up things, is for the federal government to provide the resources, the state to take control from the locals, and the governor to be nominally in charge while the federal government provides somebody with the technical expertise to do it. What else have we learned here? You really can't evacuate a city. If you look at Rita, even after Katrina, there were more people left in Houston than there were in New Orleans. Okay, why is that? Turns out Houston's just a much bigger city and with almost the same amount of interstate capacity. This was an example of where people had done very good studies about who would be left behind in terms of a voluntary evacuation. And New Orleans is reasonably good in terms of a city with public transportation, but they forecasted 100,000 people and that they would be poor and elderly and those people who didn't want to leave. And what would it have taken to get the people out? It would have taken a large-scale police and National Guard effort to go door to door and buses to take them out. And that was never going to happen given the resources available. Okay. The sad thing here is that post 9/11, the country is actually in no better shape, in fact, much worse shape to respond to large-scale natural disasters. In part, that's because FEMA was allowed to completely deteriorate while the emphasis was on terrorism, even though the thought was that the terrorists would cause disasters. And various groups have been put together, and for instance, when you said, what could terrorists do cheaply? Say, start Western wildfires and aim them at cities. So, I mean, almost all these sort of things have posed sort of large-scale disasters, and yet the agency, the part of Homeland Security that needs to respond to that, has just been effectively gutted during the last several years. The thing that's always been pointed out is the need for communications. And at some level, this is the thing that Homeland Security could have imposed from the top and paid for. You can also have pre-disaster contracts for disaster response. One issue continues to revolve around the use of the National Guard. What's always going to happen in these large-scale, large-area disasters is that the impacted state is going to be unable to respond, and that's in part because the National Guard in that state got wiped out. There are great, I should say, sad stories about the National Guard in New Orleans. They had to retreat to higher grounds. Their vehicles got flooded and had to be abandoned. What could you have done if you wanted to send in the National Guard? Well, you could have had the C-130s loaded up with the Illinois National Guard lined up on the runway in O'Hare. You could have used bulldozers to clear the airfield at New Orleans, and you could have landed people within several hours after the storm passed. But you have to bring them in outside the area. The other thing you can do is use military instead of National Guard. There's a debate over whether you should use an airborne division, which is probably not the right thing. What the U.S. really needs if they want to go the military direction is probably to have a division earmarked for this. And if you think about what units they really need the military police, the engineering battalions, and the medical units. And unfortunately, if you look at the Guard, these were exactly the units that were sent to Iraq, so they weren't there. Okay, what's the likely future? New Orleans will indeed be rebuilt at great expense. It's an open question as to whether or not it should be rebuilt, at least in the particular manner that it currently is. Hurricanes will continue to hit the Gulf Coast. And unfortunately, I think our next speaker is going to tell us that not only are they going to continue to hit the Gulf Coast, but the frequency is likely to increase. The government will do better for a while. Politically, what was really surprising about what happened with FEMA is that everybody knows in one of these big disasters, this is the chance to look good and shine by doing the right thing. And a lot of it's just a PR effort. At the beginning of one of these disasters, there are two things that you have to do. You need to put the forces into the city to restore law and order, and you need to appear to be there. Anyway, they're unlikely to screw up in that fashion again. The policies, though, that led to a lot of this building in floodplains, they're going to continue to build. Are they going to require flood insurance? No, what's going to happen is if there's another big flood where a lot of people are impacted, they will pay. Are they going to change water projects? Now this levee system, the shipping canals are a mess. And unfortunately, the wetlands, which for hundreds of years protected New Orleans from this sort of disaster, are being lost at a fairly rapid rate. So every year, New Orleans will be more and more vulnerable. Okay, that's the end.
My task is to say something about the outlook for the future, given the fact that we know the climate is changing. This is an interesting picture of Katrina, and the color code is ocean surface temperature, with the warmest temperatures in the yellow and orange colors. And as has been stressed, that's a necessary condition for hurricanes. A hurricane is physically rather simple once it forms. There's a lot we don't understand about how it forms, but we do know, and you heard about it in the first talk, that it's essentially a heat engine whose fuel supply is the warm water of the upper ocean. We know that there's a threshold temperature of around 79 or 80 degrees, below which hurricanes don't form. So it's a necessary condition to have a warm ocean, but it's not a sufficient condition. There's lots of places where the ocean is that warm, where hurricanes don't form. And we know that there are many, many circumstances that favor hurricanes. For example, the presence of a little perturbation in the circulation, the right structure of temperature and wind as you go in the atmosphere from the surface up to the top. But it's a very difficult, essentially impossible task so far to predict hurricane formation. Lots of proto-hurricanes, little storms form that don't intensify into hurricanes. Nonetheless, we do know a great deal about hurricane physics, and we have good theoretical and computer modeling grounds to have suspected that in a warming world, and we're all in a warming world today, that hurricanes would increase in strength, not necessarily in frequency. We might not have more hurricanes, but it had been forecast that the strong hurricanes would get stronger and there would be more strong hurricanes. We've got some new results to show you. I'm going to summarize some recent research done mainly not at Scripps, but partially at Scripps. And I'll show you at the end where these results come from, but this is high-quality, peer-reviewed, up-to-the-minute scientific published research. And remarkably, the energy released by hurricanes has been going up in recent decades due to two factors. There are both an increase in the sustained maximum wind speed and about a 60% increase, a major increase in the lifetime or duration of storms. That 15% increase in wind speed is large because the damage that hurricanes do goes up non-linearly with wind speed. For you mathematicians, it goes up roughly as the cube of the wind speed. Here's some striking results. There are two curves on this graph. The solid one is a measure of the sea surface temperature in the tropical Atlantic, and the dashed line is a measure of the damage done by hurricanes, or the potential damage as a function of this duration and maximum wind speed. And you can see the lines run from 1930 up till the present, and there's been ups and downs over most of that time, but in the last 15 or 20 years or so, there's been a remarkable upsurge in both the average sea surface temperature and in the strength of the hurricanes in the Atlantic, measured the way I just mentioned. The correlation here is extraordinary. This is the same kind of plot for the Atlantic plus the Western Pacific, another region which you'll remember from the earlier maps is prone to generate many hurricanes. And here too you see a large increase in recent years above the long-term norm, and a remarkable correlation between sea surface temperatures and the potential damage intensity of hurricanes. It's a fact that the ocean surface temperature globally has increased by about 0.5 degree Celsius or 1 degree Fahrenheit over the last 35 years or so, and this increase has occurred in nearly all the ocean basins of the world. So from the hurricane's point of view, its fuel supply is increasing. Here are curves of the summer sea surface temperature. Summer is the hurricane season. Over several ocean basins. The codes here, the red line at the top is the North Indian Ocean, the green line the Western Pacific, then below it the Southern Pacific. The black line doesn't stand for Scripps Institution of Oceanography, but Southern Indian Ocean, and Eastern Pacific and Northern Atlantic. And except for the southern Pacific Ocean, there's a statistically significant upward trend. The temperatures on the left are in Celsius degrees, so when you see an increase of about half a degree Celsius, which is typical, as I just said, over almost all the ocean basins, that's about a degree Fahrenheit, and that's significant from the point of view of hurricane intensity. I'll remind you of the difference between the two strongest categories of hurricanes. Category 4, it's an arbitrary scale, has peaks between 131 and 155. These are sustained winds, that is not just a gust. And a Category 5 is over 155. There's been research very recently published on how many of the hurricanes are Category 4 and 5. And over the satellite era, we've seen an extraordinary increase in the fraction of storms that are Category 4 and 5. It turns out that the number of hurricanes hasn't increased much. It's simply that the proportion of storms that are the strongest storms has increased very dramatically. And I'll show you a couple of graphs of that. What you're looking at here, again, the horizontal axis is time from 1970 until near the present. And there are several things shown here. The top line on here, the black line marked maximum wind speed, has a scale over on the right. And it shows that, remarkably, the maximum wind speed observed in hurricanes hasn't changed very much over this period of about 35 years. Instead, you see more or less random wiggles up and down, but the maximum wind speed is in the neighborhood of 80 meters per second, which is upwards of 160 miles per hour. And so it's the Category 5 limit, you might say. Category 1, the weakest storms, Category 2 and 3 stronger, Category 4 and 5, the monstrous storms. And you can see there's been a decrease, the blue line, in the Category 1 storms. The dashed lines show their historical norms. So Category 1 in recent years has decreased in number below its historical average, but Category 4 and 5, as I said, has approximately doubled from about 40 storms per pentad here, these are 5-year periods, up until about 80 storms or a little bit more lately. So there's been a remarkable increase globally, and once again, these are our satellite data. Data have been cleaned up, reputable people have done it, so you're not seeing an artifact of better observing systems today or changes in data processing or anything like that. As I said, the number of absolute storms, with the exception of the North Atlantic, hasn't changed much, and so what you're seeing with that increase in the absolute number of the Category 4 and 5 storms is simply an increase in the percentage of all storms that belong to these strongest storms, going from below 20% early in the record period up until something in the neighborhood of 35% most recently. So we have observational confirmation of what we had theoretically expected, namely that the fraction of storms that will be strongest has increased, although the actual limit, they might say the strongest hurricanes ever observed, don't seem to have increased. Now, as you may have heard, the world's been warming up, and as you may know, you and I are part of the cause. And what's less widely known is that the extra heat that comes largely through strengthening the greenhouse effect through burning fossil fuels, and this is no longer conjectural, it's widely accepted, it's a mainstream scientific result, it's much less controversial than some parts of the press would have us believe. The scientific community has long ago come to the conclusion, settled conclusion, that the world is warming, has noticeably warmed, and that the largest part of the warming in recent decades is due to human activities, particularly the consumption of fossil fuels that increases the greenhouse effect. What's not widely known is that the great majority of the heat that the Earth has retained because of the stronger greenhouse effect that it would otherwise have lost to space has gone into the ocean. Part of that heat has gone into the atmosphere. That's why surface temperatures in the lower atmosphere are warmer than they were, higher than they were. But 84% is one estimate from the leading authorities, is that heat is stored in the ocean. And we have clear observational evidence of this now. It's not conjectural. Here are, for the Atlantic, measures of an increase in heat content here. This is an odd unit to most of you called joules, and it's a metric unit. And there are three colored lines here. The red line, the top 1,000 meters, about top 3,000 feet of the ocean, then the 2,000 meters and 3,000 meters. You can see that most of the warming has occurred in the upper kilometer, 1,000 meters, or upper 2 kilometers of the ocean. But there's been a very significant increase over the last 50 years or so. This is the same kind of picture for the world. We previously saw the Atlantic, and again you see this, this remarkable upward trend. The Atlantic, by the way, contributes largely to this trend. The oceans differ because of many reasons, including different circulation patterns. So what we have seen in these kinds of things is a congruence between the predictions that we'd made theoretically and with computer models and the observations that we're making in the ocean as well as in the atmosphere. There's the footprint, you might say, the fingerprint, if you like, of human actions is discernible now in observations. And here's an extraordinarily telling set of results that was in fact produced by a consortium of scientists led by a Scripps scientist, my colleague Tim Barnett. What you're looking at here, and I don't have time to go through the details, but in each case here you're seeing temperature on the horizontal scale with 0 represented by this vertical line, and depth here from the surface down to about 700 meters. So a substantial depth of the upper ocean in each of the major basins. The green lines here were predictions from an ensemble of computer model runs showing what kind of warming we could expect, and the red lines are observations for each of the oceans. So with almost no exceptions, we see that although the patterns are very different in the different basins, we are seeing a congruence, a coherence, a resemblance between the observed in the red and the predicted in the green band. This is much too complicated to be fortuitous, and it couldn't have been tuned in by modelers trying to cheat, because in fact most of these observational data weren't made when the models were constructed. But we see here a resemblance that's so strong, and the details, the supporting data behind this are even more convincing, that we don't have any doubt that the warming is there, it's to great depth, and it matches the fingerprint we'd expect from an increase in the greenhouse effect and other human actions. All the results I've shown you so far came from these 4 papers, all of which were published in top-class peer-reviewed scientific journals this year. There's a great deal of work that underpins this, but there have been these spectacular new results in recent weeks and months, and I wanted you to see something of them. I'm almost done. I think it's fair to say that we can reasonably conclude that the observed increase in the destructive power of hurricanes, which is again unmistakable, is linked to warmer oceans. We have theory and modeling results to support that, and thus is mainly due to human activity. It's likely that the trend will continue, but I want to emphasize that there's a great deal we don't know about hurricanes. It's been mentioned that we've made a great progress in predicting their track. The Operational Hurricane Forecast Center, run by the government, by NOAA, is very good at that. There's made a lot of progress in predicting hurricane tracks, but we are less good at predicting hurricane intensity. One reasonable conjecture, it seems to me, is that the intensity forecasts have been difficult because we didn't have detailed a priori knowledge of the vertical structure of temperature in the water over which the hurricane would pass. As has been mentioned already, the hurricane is self-destructive in that it's fueled by warm water, but the winds churn up the ocean, and the mixing in the ocean brings cooler water to the surface, which rapidly limits the energy of the hurricane. That's one reason why traditionally a rule of thumb has been that a fast-moving hurricane was a more dangerous one, because it moved over fresh, new warm water with the same, with you might say, a sufficient speed to make up for the cold wake that it was leaving behind. If, as you have seen here, the warmth that's occurring in the oceans now is mixed to depth, and if we combine that with highly variable local conditions like the loop current in the Gulf of Mexico that was mentioned, it seems likely that we may see part of the intensification due to that. In fact, although we predicted the intensification, we didn't predict its magnitude. The storms have become stronger. We've gotten more strong storms, but at a greater rate than might have been thought, with the rather modest increase so far of about 1 degree Fahrenheit in ocean surface temperature. So research is going on to look for the reason why the nature is reacting more intensively, you might say, more positively fed back than had been predicted. And that's one conjecture. A great deal is not known about hurricanes. One of the unknown questions is how the climatology of hurricanes change. And The reinsurance companies, I can tell you, as well as the oil companies with vulnerabilities over hurricane-prone regions, are very interested in this. So does the hurricane season extend? Can we expect hurricanes earlier or later in the year? Does the geographical region vulnerable to hurricanes change with time? Can the number of hurricanes change? What other aspects of climate change beside ocean surface temperature that bear on hurricane formation and tracking and intensification will change? These are areas for a great deal of research. This is Hurricane Linda. Hurricane Linda did not strike San Diego, although it was forecast for a while that it might. It was a Category 5 hurricane, and you're lucky that it didn't make landfall. Linda was in 1997, and so I'm not predicting hurricanes in Southern California. I'm just saying they have occurred. The ocean is warming up. El Nino, which produces warm water off the coast, as you know, favors these so-called Baja hurricanes. And rising sea level, another sure consequence of climate change because of thermally expanding water and melting ice on land, also increases the potential for damage. The outlook for the future is more of the same. It's not right to say, it's my final remark, not right to say that global warming caused Katrina. That's not a responsible statement. What one can say, what is scientifically defensible, is that as the world warms, as the climate changes, as sea level rises, as the area prone to temperatures that we know are needed in the present climate for hurricane formation increases, then the odds change. We are loading the dice. We are increasing the likelihood of strong storms, and therefore it depends on whether or not you feel lucky. Thank you.